Hello and welcome to IEEE Soft Robotics podcast. In this podcast, we're going to interview researchers from both academia and industry about their work, thoughts, spectrum, and more beyond that. This is Marwa Edwini, and I hope you will find this podcast useful. If you would like to connect with us, simply send us, and we will be happy to hear from you. And here is my interview. Thanks. Hello and welcome to IEEE Soft Robotics podcast. Hello, Alex. Thanks so much for your last podcast. Such an honor to have you. So
thank you for having me.
Thank you. So I'd like to ask you first, I would like to define or introduce yourself for audience when you first time listening to you.
Okay, so I'm Alex Alspach. I lead the Tactile team at Toyota Research Institute, also called TRI. And I was one of the lead developers on the Punyo bubble gripper from a mechanical engineering standpoint.
Mm-hmm. So first of all, congratulations for the new release today. It was also new soft robot gripper. So first of all, I would like to ask you if you'd like to maybe introduce what's actually the software gripper robot here, design, maybe the first step about the project.
Yeah, so the project's been going on for a while. It's gone through many iterations from a big bubble that some have seen years ago to what's now the soft bubble gripper. And it's extremely exciting to not only be able to use these in-house, but to actually share today the design source files and full build instructions for our gripper with the public. We're really excited that other research institutions and even aspiring roboticists and hobbyists can visit our website and download the files. And the website is punyo.tech, punyo.tech.
But maybe I'm just ask you the first question. I think that's something in soft robotics we speak all the time about. Why the translation from what we do in the lab or to real world applications sometimes it's challenging. And if you can pinpoint what the challenges you think so that we can have this kind of product that can be used in our daily life situation, like home, for example, what you do. So if you can tell us about why so challenging.
Sure. So let me start off with some background. So Toyota has been using state-of-the-art robots to build cars for years. And that's a highly controlled environment, a factory where robots just need to be strong and durable and consistent. And that's, that takes a lot of engineering, and it took a lot of engineering to get us to that point. But in a factory, there's no unexpected objects or situations. And when there are, we would more readily shut the whole line down rather than expect our robot to adapt. The expectations for robots in a domestic environment are very different from that. So Toyota Research is interested in working in the home alongside humans. And societies around the world are aging, and a lot of families are faced with a difficult choice regarding how to care for that older adult. And ultimately, at TRI, we've decided it's a very important goal and a very high impact achievement, if we can do it, to develop robot capabilities that can enable our older generations and eventually ourselves to age in our homes happily and independently. And one of the major challenges with robots in the home, and this is why we choose softness as an important aspect of our robots, is that our homes are incredibly varied, and that's in layout and content. Some are more cluttered than others. For instance, the mugs I have in my home might be very different than the mugs you have in your home. So even though we both have mugs, who knows what those mugs look like? They might not even be round in some cases. So for robots meant to manipulate objects in our homes, there are a lot of problems to solve before we can deal with the amount of uncertainty our robots will face. And the soft robotics community knows very well that you put a soft, very compliant hand on a robot and you've solved a lot of problems right there. So what many call mechanical intelligence allows us to reach out and grab without the robot having to think too hard to get great results. Now, traditional hard robots are tried and true, and they're based on decades of engineering. The soft robotics community is still learning where their tech fits, and we're still learning like what materials are available. It's a vast place. Soft roboticists have a lot of freedom, a lot of room for creativity, but we also need to invent new fabrication techniques, and we need to test the durability of these things, because it's not like a typical big piece of aluminum that you run FEA on in SolidWorks and you just know it's going to work. So beyond that, when it comes to doing tactile or, soft robots are always meant to kind of touch the world. They crawl on the ground, or they squeeze between things, or in our case, they bump and rub and grab objects in the world. So durability is always a concern. And I think generally people think in an industrial sense, this is where soft robots fail. And maybe that's the case up until recently, but we're starting to see a lot of soft robots in picking and placing. We're starting to see a lot more hard robots put rubber on their fingertips. So I think people are catching on to the fact that, obviously rubbers can be durable. You just have to be willing to put in the extra engineering to take it from that research soft robot to that, production level soft robot.
Mm-hmm. This is a very interesting point. Maybe I will pick first the durability. Because when it comes to the material, let's speak about when we speak out. I don't know for application, if you imagine that application at our home, how many hours do you think, or the durability for these robots can be stand with fatigue, or if there's damage happening as well? I don't know if you're also planning to see how can be adaptable this damage happening in these grippers, for example. Maybe that's a concern in community as well. Yeah,
it's a concern, and we're having a lot of fun playing with the concept of it. So, we don't forget that we're in a research institute, so we can, replace our bubbles, and we don't got to worry about a million hours of use. But we've gotten, nearly 100 hours on our bubble grippers, which is way more than we expected, and I think it's way more than a lot of people expect from what's basically a balloon rubbing up against, objects in the sink for hours and hours on end. We've designed the bubble grippers in a way that if they do wear out and they're unrepairable, 4 screws and the bubble comes off, camera stays on the gripper, you put a new bubble on, and we make easily 10 to 20 bubbles at a time, just so that we have backups. And we don't use all those backups, but we have a lot of bubble grippers in the lab right now. One really cool thing that we found out, in one of those, the robot broke as you're leading up to, finishing up a paper, right? Doing the last bit of experiments. We popped a bubble, and it was on some sharp object in the sink. And, we had a bicycle sitting over on the side of the lab, looked over the bicycle and thought, okay, we could probably patch this in the same way you'd patch a bike tube. So it's a latex membrane. We took a hole puncher and took a little tiny piece of latex, put rubber cement on it, stuck it on. That bubble lasted for the rest of the week. It didn't leak. It didn't change. We didn't have to tune the sensing or anything. It was, pretty much the same. And we have fun imagining, just like Baymax puts tape on his arm when he's leaking, we imagine a robot being able to quickly patch itself and reinflate. But there's many ways to go about this. We've chosen thin materials so that we can see a lot of what's going on from the inside, what's going on the outside. But recently we've started to think about thicker materials that maybe the sensing isn't nearly as sharp, but the durability is like tenfold, something like that. So there's a lot of balances you can play with if you want durability more than accurate sensing, or vice versa.
That's a very interesting point. In case of skin that kid, because you mentioned a really good point. But when you speak about, for example, self-healing, we have done out with material when it comes to smart material, or how you choose, maybe when you have this problem and you consider, maybe some students listening to you or people would like to choose what they do. So how you figure out that these trade-offs, for example, I wanted to, how to choose a problem and also to ask the right question and come up with this material. And also you don't have to go to a more expensive solution when it comes to sometimes, the design of the product. I don't know what kind of thought you have when you see, because in the field we have a variety of materials. We have passive material, a smart material, and now we have self-healing as well. And we speak about something simple and possible and also efficient. So how you manage to do that, if you can tell us more about that selection of the process itself.
Sure. To be honest, the Tactile team started off very small. It was one mechanical engineer, and that's me. So it was important to choose manufacturing techniques that were easy. Many of my materials are right off the shelf. So the reason we originally chose latex was because it was easy to get. We didn't have to pour it ourselves. This was back when we didn't even have a lab, when TRI first started. And you could laser cut it and cut it into all kinds of shapes and inflate it. One interesting aspect of the latex is that it is flat when it's deflated. So you can, we had a recent paper published at RoboSoft where we would let the air out of the bubbles and we could kind of get them under into tighter spaces. If you had something that was cast in that shape, it might not be able to do that as well. So there's definitely an element of sticking with what works. And we've used this latex for a while. We've built a relationship with the vendor, and they'll cut it into shapes for us if we need it, or they'll send us free samples of new things they have. They'll help us solve problems. There's definitely an aspect of that, but we realize that we really like the availability of it. Not having to make it ourselves is important for being able to really kind of fail fast and build a lot of these things and not really care when they get destroyed and not spend a week, kind of fixing them when they're built. But recently we are starting to try out other membranes, still not casting anything, although it's definitely a consideration, but we always feared that eventually we'd meet someone with a latex allergy. And now I have a friend that's prompting me to start looking into other materials like silicones and neoprenes and stuff like that.
But do you believe, maybe, I don't know if you're pushing the limit, I don't know if you think maybe in the coming year, do you believe that, because we know some materials still not yet ready to be used. Do you believe, or have ever thought that maybe using this material with these capabilities, maybe would be advantageous, maybe in the coming years? Have you ever thought about kind of material beyond what I have?
Yeah, so back to the self-healing materials, I think they're awesome. And if it really works quickly, I'd consider it. If I could just get some samples, I'd be more willing to try it out. But right now, because it's so easy to fix and replace, I have trouble dedicating the engineering time it would take to kind of test those out. But it might just because I don't know enough about their capabilities. Right now, I imagine a robot fixing itself. And if we're really building a truly dexterous robot, just like me, I go put a Band-Aid on and, protect myself. Luckily, I am self-healing, but, material is cheap.
Yeah. So when it comes to mechanical intelligence, the design of the gripper itself, when you look for the advances, we speak about sometimes just incremental advances and also as breakthrough in the field sometimes. But when it comes to design of the shape or the mechanical intelligence to the gripper, how do you figure out this kind of morphology that could be also play or go hand in hand with the sensor that you try to design and has all these features you want to do so that it could be working in a certain environment, like I mentioned, they were cup. We don't know the different shapes. Why select as a design?
You've tuned into the downside of using flat materials like sheets of latex, and that is that, for instance, with our bubble gripper, the bubble is shaped like an ellipse, and it's flat to start, and when we inflate it, it looks like that. And we don't really have much control over that. We can make it fatter, we can make it skinnier, but that apex is going to be in the middle, and it's going to inflate just like that because the material is all the same thickness. So that's a limitation of using the thin membranes and inflating them the way we are. But we do have some ability to kind of change the profile of the plate that it pumps up from. We've played with that quite a lot, and we settled on the current morphology, which is ultimately ellipsoidal, so that we could simulate it. So we're using some pretty advanced soft simulation techniques at TRI that are evolving by the day. So when this gripper was first developed, we kind of had some limitations, like, we can do cubes, we can do spheres, and you got to make either a cube or a sphere. I'm like, could I maybe have an ellipsoid? I feel like I like that shape a lot better for getting into tight spaces, and the camera field of view is more like a rectangle than a square, so maybe that would work. And they actually developed the simulation technique for ellipsoids because the dynamicist and the mechanical engineer agreed that this shape would be doable. It'd both be doable from my end and acceptable. It would be actually achievable to simulate this from their end. So that's one of the reasons that the shape is what it is. but we've tested it and we like where we can get the bubble. You know, we started off by taking mugs and plates out of a sink and putting them in the dishwasher, sorting recycling and stuff like this. We've played with a lot of objects since, like spatulas to flip pancakes, and just playing around and seeing what we can do with this. And surprisingly, we haven't really felt the need to change the shape. You know, maybe we started to play with the inflation of bubbles, but no one's been really begging for a shape change, which is a little bit surprising to me. Maybe someone's asked for it to be smaller, and then, you know, someone comes around and asks for it to be bigger. So we are still kind of gathering experimental data on what we want this gripper to look like, but ultimately, no one's really pushing that hard on changing it because it works pretty well for the applications we've been applying it to.
Right. Okay. And why is it surprising? I don't know. What kind of thoughts do you have before you? I don't know. I'm curious. What kind of thoughts in your mind before?
Yeah. So, you know, for instance, I expected at some point we'd want the high point of the bubble gripper to be further out, you know, so that you could pick up, you know, something closer to the table. You know, if I were to try to pick this up even from my hand with the bubble gripper, we can't really do that yet. But what we can do is we can, instead of, you know, changing the bubbles entirely, we could just move the fingers a little bit, and now suddenly we can touch with the fingertips. So there's pretty simple solutions to getting some of the grasps that we're interested in without, you know, some major overhaul or some design optimization or some all new fabrication technique. It's been pretty easy to take these minor, like, you know, let's think hard. I think one of the benefits is that, you know, we have a perception and control lead, Naveen Kupaswamy, and I, you know, we argue all the time. He says it's a hardware problem, I say it's a software problem, and we meet in the middle. And it's great to be able to have this dynamic where it's not a bunch of mechanical engineers in a room trying to decide what works best, because we're never going to get to something that pleases everybody that way. So now our team has grown and we have multiple electronics engineers and mechanical engineers and everything. And, you know, we talk a lot about design review and how to make things better. And we always lean towards the kind of simpler, elegant solutions that we can enact really fast and test and make sure that we're going in a direction that works, as opposed to, you know, 6 months of full renovations and then we'll see whether it works or not. We have a very fail fast mentality, and surprisingly, this gripper has stood up to many conversations and many different tests. So I expected more iterations of it, but it's been a pretty static design. You know, besides minor tweaks that have, you know, one of the biggest changes to the gripper that's happened in the last year that made this this release possible was when we got stuck working from home. We couldn't build the gripper because we were using the nice 3D printers we had in the lab. We were using, you know, some parts that we just couldn't have access to. But having to work from home, we redesigned it to be printed on like hobbyist FDMs, you know, like the $200 3D printer. So that's why that kind of gave us the spark. You know, when a software engineer on my team made his first bubble gripper, I'm like, okay, you know, anybody could do it. And that kind of generated this this desire to say, you know what, it's not that big of a deal now to just document it and put it out there so anybody could try it out. And, you know, maybe they'll tell us what the bubble shapes need to be next to grab all the things in the world, and we'll gladly take that advice. Great.
So I'd like to go for the sensing design, because I think in the community also we have a lot of discussion about the sensing, is why it's complicated sometimes, and why sometimes we can use the sensing or maybe less relying on the feedback that's very expensive and make the software maybe more predictive to uncertainty. How do you see for you when it comes to application like that, what's the efficient way for the design of the sensing?
We've been very interested and intrigued by visuotactile sensing in general. And visuotactile sensing is basically sensing tactile with a camera. So there are folks who have done this before us. For instance, Ted Adelson's group at MIT, who makes GelSight. There's GelSlim at MIT. There's Finger Vision from CMU. And these are really cool sensors that basically, they have a rubber and they have some dots or a structure that the camera can look at. And when you push something up against them, things move, lighting changes, and you can see what's going on. This is extremely interesting to us because, number one, cameras are getting cheaper by the day. You can buy a $2, your cell phone has the tiniest camera you've probably ever seen. And these are not expensive when you go and you find them on Amazon or Alibaba or something like that. So it's really not cost prohibitive to take this route, even though it seems complex. And ultimately you get thousands and thousands of data points from these things. It's not a 4-pixel barometer stuck in rubber kind of tactile array, which are still very useful in some cases, but in the research thread that we're taking, we really just want tons of data, all the data, and see what we can do with it. So for the bubble gripper, because we've gone the visuo-tactile route, we've been able to try a lot of things that we didn't really intend to from the get-go. We built the bubble gripper thinking that shape is all we want, at least at first. We weren't thinking about much. We just wanted to see shape of the objects we were grabbing. And so we took the route of putting a depth camera in there. And again, this was a decision made to just keep things easy. I could have put a stereo camera in there. We could have had an algorithm that's making point clouds, but instead we went with something off the shelf so that we could get point clouds right out of the box, and started doing things like pose tracking and stuff that you do based on the geometry. Because we went the camera route, we were then able to look at dots on the inside, learn how to print dots on the inside and watch them move, and start doing the shear tracking that we learned from gel sight and finger vision. We started doing object classification because with a camera, you can just run, tried and true machine learning techniques from the computer vision community. So I think that, in the case of our bubble gripper using a depth sensor, it's not the cheapest option in the world, but as soon as you make the move to little tiny cameras, which are just increasingly available, this becomes a very, very affordable way to sense tactile in general. And as the compute abilities of robots just skyrockets as well, and the price of that goes down, I don't see any reason why we couldn't have a ton of cameras on a robot just doing all the tactile work.
Mm-hmm. So I'm curious to ask you about maybe the scenario. What could be an avoidable trade-off when you try to design? Maybe you mentioned that sometimes it's a hardware problem, software problem. So what could be an avoidable trade-offs you faced in this project, and you think that you can't get around it?
I think an unavoidable trade-off of the sensing techniques that we've chosen is the sheer amount of data. You wind up having to process a lot of data to get the job done. And ultimately, it's forced us to start looking into how to process all that data, how to downsample it, and how to maybe make some decisions locally at the sensor level that you could feed back to the robot. I don't think it's a bad problem to have, but it's absolutely unavoidable when you start to talk about how many pixels are coming out of a camera.
Right. And when it comes to safety, I don't know, did you imagine, you mentioned already for the hardware part, it's easy to solve if there's damage happening, but what if happened, the software side is damage happening, and how we can adapt to a scenario like that?
From a software aspect, I think there's probably a lot of work to be done in robotics in general for learning how to fail gracefully. It's one of the reasons humans are so good at being adaptable and effective in their environments. We're able to take in all kinds of information and maybe make mistakes, but we roll with it. So I think that ultimately, from a sensing side, from a sensing point of view, the amount of information that we can generate is really important. The software side can only benefit from all that information as long as they know how to use it. I think based on my experience using these sensors with machine learning techniques, I think we could very easily learn what is expected output of these things when our robot is doing a task. and what is unexpected output. And you know, from a safety standpoint, I'm sure Toyota would have a lot of opinions on how to handle this well, but the first and foremost, I'd say the robot should stop, and safety is of utmost importance. If anything's going wrong, we would absolutely have engineered it to take the safest option.
Great. So I'm curious about maybe the limitation. So the project, I don't know what kind of limitation do you have, or maybe it's still a technological roadblock, if you have any.
So I think the limitations probably still do lie in durability. Like, whereas this is durable enough for our research, and we're proud of the durability, there's a lot of work to be done before this can, you know, live with you for a year and not need too many replacements. That is something that we're thinking about, but it's not a major concern of ours, because luckily we're research and we don't have to engineer it to those standards to prove that it's valuable. I think that another limitation that we're thinking about hard is that the Punyo gripper, as it's presented in the documentation we released, is a parallel gripper. And there's a lot of more interesting degrees of freedom that a robot hand can have. And we've had great success with the parallel gripper because there's a lot of compliance in the actual bubbles. But it's worth remembering that there's other degrees of freedom out there that we could play with to get these bubbles into more interesting orientations, including the degree of freedom related to just deflating it or inflating it. So you can solve that limitation just by bolting it to a different gripper, because these fingers, you know, they pop right off the grippers we use, and we can put on something else, and we'll see what happens when this gets, you know, used by the world.
When it comes to, for example, the interaction with human, I think that's something, still very interesting how you think that's kind of interaction with human hand. If you, for example, you pick and replace something, or you hand over something, how do you see that also?
So I've had the luck of interacting with these robots a lot, and I am, you know, as the robot's parent, I am always, you know, first in the, you know, to take the caution tape away and get in there and start to like pull on things and antagonize the robot and see how robust the grasp is, for instance. And one late night, we had Naveen and I had the idea to like put one more demo into our paper and video. And we had the bright plan to hand over a mug. And the robot picked up the mug. You could see this in one of our press release videos, but the robot picked up a mug. I grabbed it, we read the shear signal and released it. And I was surprised, you know, first time it felt so natural. And that the natural aspect, I think, comes from the fact that the robot doesn't even need to react to you for those bubbles to start to flex and allow you to pull that mug just a little bit, just a tug. You know, it's not like a hard grasp. You're able to pull it a little bit before it senses and releases. And those soft aspects, I think, make the robot approachable. They make it feel like something you want to interact with, and they make it feel natural. And, you know, luckily that compliance and the ability to sense actually gives us the ability to let go and be natural and actually kind of sense in natural ways, you know, as the robot is able to be pushed and pulled on and kind of distorted to a point.
That's great. But I'm curious, do you think there's maybe a scenario, maybe you think that doesn't work well? I don't know, because I think we still have limitation in general in the field. If there's anything maybe do you think couldn't work very well for a certain scenario? I don't know if you have something you would like to share about that.
So because of the low degrees of freedom in the gripper, there's not really much in-hand orientation or something like that we could do. We've gotten around that by, say, you know, bumping up against the world. If I have this and I want to move it by a few degrees, I can knock it against the table and grasp it like this. So we've played with the idea of, you know, kind of leaning into the low degrees of freedom and utilizing the rest of the world to push and pull on things because we don't have enough fingers. I think that can be solved just by taking the plunge and starting to put this onto higher degree of freedom robots. And whereas we're not really pushing to make this technology more miniature, we could make it a bit more miniature if we wanted to and go this route. But what we're more interested in at this point is taking these bubbles off the hands and starting to put them on other places on the robot and really do tactile sensing everywhere, not just the hands.
So also I'm curious if there's any counterintuitive moment. You mentioned one thing that was surprising about design, but in general, do you think this would be the result? Do you think when you try to serve the software where it was counterintuitive to you? You didn't expect this behavior? It was counterintuitive? Did you have any moment like that?
I think we had that moment not by watching the robot, but by watching fellow humans. Over the past 2 years, we've done a lot of slow motion videos of each other and, watching us pick up spoons or load the dishwasher or, carry big heavy boxes. And I didn't realize how much I let things slip in my grasp to get them where I want them to be, or to just allow some motion when I need to. It's surprising. I think when you start to focus on what your hands are doing in general, it's not intuitive. And this is happening in places in your brain that you're not thinking about, and many people don't think about. So when we started to notice all this, what we call slippy sloppiness in the human manipulation strategy, we started to play with whether or not our bubble gripper could do that. Because, I think it's pretty much the belief that a robot should grip and just not let go until it's ready to put it down. But the ability to let things slip and slide in your grasp is something we do all the time, and it's something our robots should be able to do. And we've experimented with a lot of ways with these bubble grippers of just releasing, a little bit of pressure or opening up a little bit. And now the friction is just at the right point where things can actually rotate in the grasp. And playing with this has been really fun. It's something we didn't expect to want to happen. We always thought slip was bad. But if it's controlled slip, it's really valuable, especially when you don't have enough degrees of freedom in your gripper to really just do it on your own.
That's interesting. And do you think, I don't know, how do you see the learning in that case? Do you think, since, I don't know, how do you envision the learning process to be continual learning? And I don't know, do you envision something about designing the learning algorithm to adapt? Of course, you have that something for now to be in uncertain environment or cluttered environment, but for learning, how do you envision that could be deployed, or what kind of techniques, or how do you see it?
So my experience with machine learning people is that they just want all the data all the time. They want a ton of data. And, one of the benefits of these sensors is we have a lot of different sensing modalities, and each of them are pumping out a ton of data all at the same time. So we're still finding out which ones of those get the machine learning people the most excited. But we've had some luck playing with, very basic toy problems using machine learning, like object classification in the grasp. But one thing we're really interested in is how the robot can learn in general. How can you teach the robot? And a lot of times when you teach a task to a fellow human, you might put your hand on their hand and show them how much force to apply, or guide, their shoulders and tell them where to be. And it's exciting to know that, when it comes to learning or teaching, the robot could use this tactile information in many different ways, just like we do. And the fact that we could actually guide the robot through touch and teach it new things means there's going to be very intuitive ways of human robot interaction that are going to kind of percolate out of having tactile sensing both on the hands and maybe other places too.
Right. So since we're close to the end, I have a few questions. Maybe the first one about what could be something you and the team learned through this project. I think maybe sometimes you have missing this understanding before you started. And I'm curious what kind of things that change in you and the team, the way of thinking, the way you ask the question. If you can tell us more important point about that project, the way you guys communicate about the question and the problems.
I think the willingness to take advantage of slip, both not just being able to sense it and grip hard when it happens as an accident, but to be able to want it and utilize it and control it was one of the major things that we learned as a team. And it's definitely guided our research direction quite a bit. Another thing is that we realized that miniature is not always better. I think a lot of tactile sensing and robotics in general, they want to make their sensors tiny. And because a lot of people are doing that, we've, I think, gotten the ability from our colleagues working on gel site. They're making tiny little fingertip sensors, super high res. We learned that we don't need to be in that space also. We can rely on their incredible contributions to the community, and we can then focus on other parts of the robot body. Maybe we can make bigger sensors. And I always imagine some big like belly sensor or something, one big bubble that you can push things up against. So, whereas almost everybody's first question, and thank you for not asking this as your first question, is when is it going to be the size of my fingertip? And I say, well, we have friends that make those. And we've learned through the process that it's okay to kind of work at a bigger scale for a little while. Including, if you go back and read one of our papers, we have 2 huge kukas with 2 big bubbles on the end being, like tiny little fingers, but they're huge. And we've really kind of leaned into this. Scale doesn't matter yet. We're just trying to learn about tactile sensing, and call it a finger, call it an arm. It doesn't matter. We're sensing what we're touching, and we're doing really cool things.
That's a good point. Yeah. And what could be you and the team aspiration or expectation when it comes to what you guys doing for soft robotics community? What kind of, maybe, I don't know, engagement or cooperation? How do you see the progress of this release day? For what are your expectation or aspiration for people listening, and how they can engage more about that?
So we have a lot of relationships with various universities who know about our work, and I'm excited that they can finally build the grippers themselves, because even they didn't have access to these instructions or information besides the little tiny bit that we had in our paper. But we thought, why not release it to everybody? Because the soft robotics community is growing, and I'm just so excited to be able to help it grow and see what comes out of it. The soft robotics community is some of the most creative people out there. I think it's like arts and crafts meets robotics. I love it. So we're hoping that creativity winds up showing us, which materials are better, what shapes and sizes work even better, put these bubbles on things we never expected. That's what I really would love to see specifically from this release. But in general, what I want to see from robots is, number one, the mixing of the hard robotics and soft robotics communities. I think it's very powerful to mix those ideas, and it's great to be experienced in both of them. And when you can do that, you can start to take advantage of contact, as opposed to the last, how many decades of robotics where you only want to touch the one thing you're moving, and anything else is an accident. We want to see robots that use their whole bodies to carry big things, or to help you up the steps, or whatever it might be, to place your elbow against a wall and stabilize yourself. Just make contact with the world, understand it, and take advantage of it. That's our dream robot, is one that's not afraid to make contact.
Great. And what could be maybe the most important quality you and the team have gained? Because sometimes it seems you work very hard in the team. That what could be the most important quality do you believe that we have to maintain for the progress of the project, or in general, way of thinking?
I think our most important team quality is the diversity of our team. We have an extremely multidisciplinary team with software people, electronics people, hardware people, perception and controls people, dynamics people, and our backgrounds are also very diverse. We have experience in entertainment and consumer electronics and product design and octopus robots and all kinds of interesting things, even education, which is one of the reasons we love reaching out to the community and sharing well-written build instructions. So that diversity of thought that we have on our team really makes us think hard about the solutions we come up with before running too far with them. We do design reviews with each other. We try to understand, if I do this, how much harder does it make your job? But having all those voices in the room and having those voices willing to speak up and say what they think has been an incredible advantage that our team has been able to utilize as we build soft robots.
Great. And guess maybe finally, the best advice maybe was given to you, maybe was life changing. I don't know if you received any advices. Do you think stick to your mind? I would like to share.
I was not always into soft robotics. When I went to school, I was doing humanoid robotics, and when I graduated, I started working on robotic hands, and these hands were back drivable and compliant, and because of that, they were able to grasp anything you handed to it. And I was basically a sales guy for these hands. I built them, I wrote documentation, but I also got to travel internationally and sell them. And so, I always, what's the weirdest object you guys can bring to my table? I'll show you my robot can grab it. The person who developed that taught me about the power of compliance. And that's not strictly a soft robot, but the learnings are all the same. You need to be able to comply around your environment, but also control it to some extent, and then you can do amazing things. So when I then worked at Disney and we started building real soft robots with real bubbles, and I learned that the lightweight aspect of air-filled stuff means we can put it anywhere and not really worry about the weight of it, and you still get all that softness now, but with a whole lot less code. You add mechanical intelligence and you reduce the need for a lot of lines of code. And compliance in general does that for us. That mechanical intelligence allows us to simplify certain problems and move on to other problems. So I think just moving from hard robots to understanding the aspects that compliance can give you, and the various people who taught me that throughout my career, it's obviously changed my trajectory of research greatly. And, luckily I've been able to meet a lot of like-minded people along the way that agree with me and are willing to try that out.
That's a good point. Thank you for sharing that. I don't know if you have any final words you'd like to say, or about the also new release. If you have any final words you'd like to say for closing. Yeah, I don't know if you have any final words.
My final words would just be, check out our new website for the Punyo gripper. Download the files, read the instructions, reach out. There's an email address on there where you can contact the two authors, which are me and our intern Siha Junhai, who wrote all the documentation. But we're very willing to hear what you think of the site, or what you think of the instructions, everything. And even if you don't have comments about what you see on that site, reach out anyway, because we are always looking for interested parties. We're always looking for interns and even full-time employees. So if you're interested in what we're doing, please be in touch.
Thanks so much, Alex. It was such an honor to have you on this very, very good project. I think congratulations, and I wish more people were engaged in that and more students as well. So thank you once again for your time. I deeply appreciate it. Thank you.
Thank you so much.